How does electrolytic capacitor work in electronic circuit? Electrolytic capacitors are a type of capacitor that uses an electrolyte as the dielectric. They are widely used in electronic circuits, particularly in applications that require high capacitance values and the ability to handle relatively high voltages. Here are some key characteristics and features of electrolytic capacitors. Dielectric material. Electrolytic capacitors use an electrolyte, which is typically a conductive liquid or gel-like substance, as the dielectric. The electrolyte interacts with a metal oxide layer on the electrode to form a thin insulating layer. Polarized capacitors are a type of capacitor that has a specific polarity, meaning they have a designated positive plus symbol and negative minus symbol terminal. These capacitors are also referred to as polar capacitors or electrolytic capacitors. Unlike non-polarized capacitors, polarized capacitors must be connected in the correct orientation in a circuit to ensure proper functionality and prevent damage. Here are some key characteristics and considerations regarding polarized capacitors. Dielectric material. Polarized capacitors typically use an electrolyte as the dielectric material. This electrolyte interacts with the anode and cathode electrodes to form a thin insulating layer. Polarity. Polarized capacitors have a clear polarity, meaning they have a positive terminal and a negative terminal. The positive terminal is connected to the anode, while the negative terminal is connected to the cathode. Electrolytic capacitors. The most common type of polarized capacitor is the electrolytic capacitor. Electrolytic capacitors use an electrolyte soaked in a porous material as the dielectric. The anode is typically made of aluminum in aluminum electrolytic capacitors, or tantalum in tantalum electrolytic capacitors. Voltage polarity. It is crucial to connect polarized capacitors in the correct polarity. Reversing the polarity can lead to the breakdown of the dielectric layer, electrolyte leakage, capacitor failure, or even damage to other components in the circuit. Capacitance and voltage ratings. Polarized capacitors come in various capacitance values, ranging from microfarads, F, to farads, F. The voltage rating indicates the maximum voltage the capacitor can safely handle without failure. It is important to select a capacitor with a voltage rating that exceeds the operating voltage in the circuit to ensure safety and reliable operation. Applications. Polarized capacitors, especially electrolytic capacitors, are commonly used in applications that require higher capacitance values and the ability to handle relatively high voltages. They are widely used in power supply filtering, audio systems, motor drives, lighting ballasts, and other electronic applications where larger capacitance values are needed. It is crucial to follow the manufacturer's guidelines and markings on polarized capacitors to ensure correct polarity during installation. When using polarized capacitors, always double-check the capacitor's polarity and connect it accordingly to prevent damage and ensure proper functioning of the circuit. High capacitance values refer to capacitors that can store a large amount of electrical charge. Capacitors with high capacitance values are commonly used in various electronic applications where significant energy storage is required. Here are some key points about high capacitance values. Definition: capacitance is a measure of a capacitor's ability to store electrical charge. It is measured in farads, F, or its multiples, microfarads, nanofarads, picofarads. High capacitance values typically range from hundreds of microfarads, F, to farads, F, or even higher. Energy storage: capacitors with high capacitance values have the ability to store a larger amount of electrical energy. This energy can be discharged quickly when needed, making them suitable for applications that require short bursts of high power, such as pulse circuits, power supplies, or energy storage systems. Power filtering and smoothing: high capacitance capacitors are commonly used in power supply circuits for filtering and smoothing applications. They help stabilize the voltage output, reduce voltage ripples, and provide a steady supply of power to other components in the circuit. Time constants: capacitors with high capacitance values have longer time constants, which affect their charging and discharging rates. The time constant is the time required for the capacitor to charge or discharge to approximately 63.2% of its maximum voltage or current. Longer time constants can influence circuit behavior, such as the response time or the ability to store energy over a longer duration. Size and form factors. Capacitors with high capacitance values tend to be physically larger due to the need for larger electrode surface areas or additional dielectric layers. They are available in various form factors, including radial leaded capacitors, axial leaded capacitors, and surface mount technology (SMT) capacitors. The size and form factor of high capacitance capacitors should be considered in circuit design, particularly in space-constrained applications. Electrolytic capacitors. Electrolytic capacitors, such as aluminum electrolytic and tantalum electrolytic capacitors, are commonly used to achieve high capacitance values. They can offer capacitance values ranging from hundreds of microfarads to several farads. These capacitors are polarized and have specific voltage ratings and limitations that must be considered in circuit design. Application examples. High capacitance capacitors find application in a range of devices and systems. They are used in power electronics, audio amplifiers, motor drives, energy storage systems, uninterruptible power supplies, UPS, and other applications that require energy buffering, power conditioning, or large energy storage. When selecting high capacitance capacitors, it is important to consider factors such as voltage ratings, physical size, temperature stability, and other specifications relevant to the specific application. Proper consideration of these factors ensures optimal performance and reliability in high capacitance applications. Voltage rating is an important specification when considering electrolytic capacitors. It indicates the maximum voltage that a capacitor can safely withstand without experiencing breakdown or failure. Exceeding the rated voltage can lead to electrolyte leakage, capacitor failure, and even possible explosion or venting of gases. When selecting an electrolytic capacitor for a specific application, it is crucial to choose a capacitor with a voltage rating that exceeds the expected operating voltage in the circuit. This ensures a safety margin and prevents voltage stress on the capacitor. Electrolytic capacitors are available with a range of voltage ratings to suit different applications. The voltage rating is typically specified in volts, V, or sometimes in direct current, DC voltage, example 16 VDC. The voltage ratings can vary widely, ranging from a few volts to several hundreds of volts, depending on the specific capacitor type and size. It's important to note that operating a capacitor near or at its maximum rated voltage for prolonged periods can reduce its lifespan and reliability. To ensure long-term performance, it is generally recommended to operate capacitors well below their maximum rated voltage, allowing for voltage spikes or variations in the circuit. When designing a circuit or selecting an electrolytic capacitor, it is crucial to consider the required voltage rating based on the specific application and operating conditions. Choosing a capacitor with an appropriate voltage rating helps ensure safe and reliable operation while avoiding potential damage to the capacitor and other circuit components. Capacitance stability and equivalent series resistance (ESR) are important factors to consider when working with electrolytic capacitors. Capacitance stability refers to the ability of a capacitor to maintain its specified capacitance value over different operating conditions, including temperature, voltage, and aging. It is an important characteristic, particularly in applications where precise capacitance values are critical. Aluminum electrolytic capacitors. The capacitance of aluminum electrolytic capacitors can be affected by temperature variations and operating voltage. Their capacitance may decrease with increasing temperature and voltage. In addition, aluminum capacitors may experience a gradual decrease in capacitance over time due to aging and the gradual breakdown of the dielectric oxide layer. Tantalum electrolytic capacitors. Tantalum capacitors generally offer better capacitance stability compared to aluminum electrolytic capacitors. They have lower temperature coefficients of capacitance, which means their capacitance is less affected by temperature variations. Tantalum capacitors also exhibit less capacitance change with voltage compared to aluminum capacitors. Equivalent series resistance (ESR) is the internal resistance that exists in a capacitor due to the combination of its physical components and the properties of the dielectric material. It represents the energy losses and dissipation within the capacitor. Aluminum electrolytic capacitors. Aluminum capacitors typically have higher ESR compared to tantalum capacitors. The ESR of aluminum electrolytic capacitors can limit their performance in high-frequency applications. Higher ESR can lead to power losses, reduced filtering efficiency, and increased heat generation. Tantalum electrolytic capacitors. Tantalum capacitors generally have lower ESR compared to aluminum capacitors. They offer lower resistance to the flow of alternating current, AC, making them suitable for applications that require low ESR values, such as high-frequency circuits. Low ESR helps maintain better energy efficiency, reduce voltage drops, and improve the performance of circuits operating at high frequencies. It's important to consider capacitance stability and ESR when selecting electrolytic capacitors for specific applications. The required capacitance stability and ESR characteristics depend on the application's frequency range, voltage requirements, and overall performance goals. Careful consideration of these factors helps ensure the capacitor's reliable operation and compatibility with the circuit's requirements. Aluminum electrolytic capacitors and tantalum electrolytic capacitors are two common types of electrolytic capacitors. While they share some similarities, there are notable differences between them in terms of construction, characteristics, and applications. Here's a comparison of aluminum and tantalum electrolytic capacitors. Construction. Aluminum electrolytic capacitors. These capacitors consist of an aluminum foil electrode, which serves as the anode, and a cathode electrode separated by a paper or synthetic material soaked in an electrolyte. The anode is covered with an aluminum oxide layer that acts as the dielectric. Tantalum electrolytic capacitors. Tantalum capacitors have a tantalum metal electrode as the anode and a conductive polymer or electrolyte as the cathode. The tantalum anode is coated with tantalum pentoxide, Ta2O5, which serves as the dielectric. Capacitance range. Aluminum electrolytic capacitors. Aluminum electrolytic capacitors offer a wide range of capacitance values, typically ranging from a few microfarads, F, to several thousands of microfarads, MF. They are available in both low voltage and high voltage variants. Tantalum electrolytic capacitors. Tantalum capacitors have relatively smaller capacitance values compared to aluminum electrolytic capacitors. They usually range from a fraction of a microfarad to a few hundred microfarads. Tantalum capacitors are often used in applications where space is limited, and higher capacitance values are not required. Voltage rating. Aluminum electrolytic capacitors. Aluminum capacitors are available with various voltage ratings, ranging from a few volts to several hundreds of volts. They can handle higher voltage levels compared to tantalum capacitors. Tantalum electrolytic capacitors. Tantalum capacitors generally have lower voltage ratings compared to aluminum electrolytic capacitors. The voltage ratings for tantalum capacitors typically range from a few volts to several tens of volts. Size. Aluminum electrolytic capacitors. Aluminum capacitors tend to be larger in physical size compared to tantalum capacitors. They are available in radial and axial lead packages and are commonly used in through-hole mounting on circuit boards. Tantalum electrolytic capacitors. Tantalum capacitors are known for their compact size and low profile. They are available in surface mount technology, SMT, packages, making them suitable for smaller and more space-constrained electronic designs. Temperature stability. Aluminum electrolytic capacitors. Aluminum electrolytic capacitors generally have moderate temperature stability. Their capacitance can vary with temperature, especially at higher temperatures. Tantalum electrolytic capacitors. Tantalum capacitors offer better temperature stability compared to aluminum capacitors. They exhibit more stable capacitance values over a wide temperature range. ESR, equivalent series resistance. Aluminum electrolytic capacitors. Aluminum capacitors have higher equivalent series resistance, ESR, compared to tantalum capacitors. The ESR of aluminum capacitors can limit their performance in high-frequency applications. Tantalum electrolytic capacitors. Tantalum capacitors typically have lower ESR, making them suitable for applications that require low ESR values, such as high-frequency circuits. Applications. Aluminum electrolytic capacitors. Aluminum capacitors are commonly used in power supply circuits, audio amplifiers, and applications that require higher capacitance values and higher voltage handling. They are also used for energy storage, filtering, and decoupling in various electronic devices and systems. Tantalum electrolytic capacitors. Tantalum capacitors are often used in compact electronic devices, mobile phones, portable electronics, and applications where space is limited. They are suitable for circuits that require smaller capacitance values and lower voltage ratings. Tantalum capacitors are also known for their low leakage current and stability, making them suitable for precision and low-power applications. It's important to select the appropriate type of electrolytic capacitor based on the specific requirements of the application, including voltage rating, capacitance, size constraints, and temperature stability. Applications. ChatGPT. Electrolytic capacitors find applications in a wide range of electronic circuits and systems. Here are some common applications where electrolytic capacitors are used. Power supply filtering and decoupling. Electrolytic capacitors are widely used in power supply circuits to filter out noise, ripple, and voltage fluctuations. They help stabilize the power supply by smoothing the output voltage and reducing high-frequency noise. They are commonly placed at the input and output stages of power supplies. Audio systems. Electrolytic capacitors are used in audio systems, such as amplifiers and speakers, to couple and decouple signals, filter out unwanted frequencies, and stabilize voltage levels. They contribute to improved sound quality, reduced distortion, and better performance in audio equipment. Motor drives and inverters. Electrolytic capacitors play a crucial role in motor drives and inverter circuits, which are used in various applications like industrial automation, electric vehicles, and renewable energy systems. They provide energy storage and help smooth out voltage and current fluctuations, ensuring stable operation of motors and power electronics. Lighting ballasts. Electrolytic capacitors are employed in lighting ballasts, which are used in fluorescent lamps and high-intensity discharge (HID) lamps. They help regulate the current and provide stable voltage for proper lamp operation. Power factor correction (PFC) circuits. PFC circuits are used in power electronics to improve the power factor and efficiency of electrical systems. Electrolytic capacitors are utilized in PFC circuits to store energy and help shape the input current waveform. Switching power supplies. Electrolytic capacitors are used in switching power supply circuits to store energy, regulate voltage, and reduce ripple currents. They contribute to the overall efficiency and performance of the power supply. Automotive electronics. Electrolytic capacitors are found in various automotive electronic systems, including engine control units, ECUs, infotainment systems, lighting systems, and more. They are used for power supply filtering, voltage regulation, and decoupling purposes in these applications. Industrial electronics. Electrolytic capacitors are used in industrial electronics equipment like motor drives, robotics, control systems, and factory automation. They provide energy storage, stabilize voltage levels, and ensure proper functioning of these systems. Uninterruptible power supplies. UPS systems use electrolytic capacitors for energy storage and smoothing out voltage fluctuations. They provide backup power in case of a power outage and help maintain continuous operation of critical equipment. Electronic appliances. Electrolytic capacitors are present in various household appliances such as televisions, refrigerators, air conditioners, and washing machines. They are used for power supply filtering, voltage regulation, and energy storage in these appliances. These are just a few examples of the many applications where electrolytic capacitors are commonly used. The high capacitance values and voltage handling capabilities of electrolytic capacitors make them suitable for applications that require energy storage, power conditioning, and voltage regulation. It's important to note that electrolytic capacitors have limitations and should be used within their specified ratings and conditions to ensure reliable operation and prevent potential failures.